Okay, so last time we talked about all sorts of aromatic stuff. We ended on aromatic heterocycles and my nasty resonance structure drawing, which I won't put back up on the screen for my own ego. So we're mostly going to talk about reactions of aromatic compounds today, and even after we finish that, then the whole next chapter is all about reactions of aromatic compounds. So another little class, I think it's not a little class, it's very important, of aromatic compounds are these polycyclic aromatic compounds, PAHs, polycyclic aromatic hydrocarbons, and they're just fused benzene rings. You can basically just put these together like puzzle pieces. You can add additional benzene rings out here, and you can basically make a big web of carbons, basically. And a lot of that is what causes smog, because burning of fuels causes a lot of these to be released. The small ones are not too bad, but the big ones just turn into particulate matter in the air, which is kind of nasty. So there's also some interesting uses. There's a research group where I did my PhD that used these molecules, especially the bigger ones with like 5 or 6 rings, and they did some crazy synthesis stuff to them, which I thought was cool. But anyway, so those are polycyclic aromatic those molecules. Okay. So reactions at the benzylic position. Okay, so what's the benzylic position? Well, the benzylic position is any carbon right next to the aromatic ring. So and so the main thing that differentiates the benzylic position from any other random carbon atom in the rest of the molecule is that a lot of the transition states and intermediates and products that are formed in those reactions have some sort of resonance stabilization with the benzene ring. And so that makes them a little bit different, although as you'll see here, they do undergo a lot of reactions that aren't particularly unusual for just like a regular alkane type carbon atom. So the first reaction we can do is oxidation. So sort of a classic oxidizing agent is chromic acid. So if we have some alkyl benzene like that, and we treat it with chromic acid, and the way you actually make that is take some sort of dichromate salt, potassium or sodium dichromate, and dissolve it in sulfuric acid. Obviously, that's a pretty harsh oxidizing agent. And what it's going to do is go straight to benzoic acid. So, of course, you'll notice that we've got 1, 2, 3, 4 carbons on that side chain, and we're going to rip all of them off except one and just leave a carboxylic acid there. So we lose most of that carbon chain. Or you can use potassium permanganate. A really classic reaction is to take toluene and react it with an aqueous solution of permanganate. What you actually get out of that reaction first is benzoate, and then you have to acidify it, maybe with some hydrochloric acid or something like that. To get the carboxylic acid. But same transformation. And if you were to do that reaction with a longer chain on the benzene ring, you would have the same thing where it cuts off everything except for one carbon atom. Now, this will not happen if there's no hydrogens to remove in order to do an oxidation. So if you've got a quaternary carbon there at the benzylic position, and you try to oxidize it with one of those reagents, you're not going to get any oxidation. In practice, we don't use these reactions very often, mostly because if you've got a large molecule and you treat it with one of these really harsh oxidizing agents, you're just going to tear everything apart. But for small molecules like this, you can do this in the laboratory. Another reaction we can do is free radical bromination. This is pretty useful. So if we've got a compound like that, we can treat it with NBS. Do y'all remember what NBS is? N-bromosuccinimide. It is that guy, and it's really good at generating bromine radicals, and so you can do radical bromination. Right there. And maybe previously you've seen free radical bromination happening at all sorts of different places. It's kind of a hard reaction to control, but fortunately in this case, if you've got a benzylic carbon, you can get this to work and be pretty selective. And this is so when you've got a radical on that carbon, just like if you've got a positive or negative charge, you have resonance stabilization with the ring, and that makes it more likely for the reaction to happen at that position rather than one of these other carbons. So, kind of for the same reason, we can do SN1 and SN2 reactions at the benzylic position. So we treat something like this with water, maybe some acid too. We can substitute the bromide for an OH group. For SN1, we've got to have at least a tertiary alkyl halide, and we do in that case. But if we have an alkyl halide that's less substituted, then you can do an SN2 reaction and accomplish roughly the same thing. Even better than substitution at benzylic positions is elimination. And the great thing about doing an elimination at a benzylic position, so here we'll do an E1 reaction, or if we have a slightly different starting material, we can do an E2 reaction. And the good thing about this is when we oh, no, JK. Need a hydrogen there. That's wrong. Okay, sorry. When we do this elimination, eliminating either water or HBr, we get that double bond. And fortunately, in both cases, that double bond is conjugated to the rest of, to the aromatic system. And so that gives us another level of stability. And so if you've got, say, an instance where you have multiple different places that could possibly undergo an elimination reaction in your molecule, you're far more likely to have that reaction take place at the benzylic position because of this resonance stabilized alkene at the end. Questions on reactions at the benzylic position? This is just a brief survey, but it's good to know that these can happen. Okay, so hydrogenating or reducing benzene down to cyclohexene is not a super practical thing to do, mostly because cyclohexane, did I say cyclohexene? Cyclohexane is just about as abundant as benzene is, but if you've got something in your molecule and you need to get rid of a benzene ring, then this can be practical, I guess, although it's not very often used because of the conditions that you need. You need 150 degrees Celsius and 100 atmospheres, which if you have anything even remotely sensitive attached to your molecule, it is going to die in that reaction, and so you'll just have some black sticky tar. But if you've just got benzene, then yes, you can do that and get cyclohexane if you really want to. Not super useful, however, if you've got an aromatic system and attached to it somewhere, even like this in resonance with the aromatic ring, is an alkene of some kind. You use a slightly different catalyst. You can do this at room temperature and only at very mild pressure, so twice atmospheric pressure, mostly so the hydrogen doesn't float away. You can selectively hydrogenate just the side chain. So you can, in fact, hydrogenate an alkene when you have an aromatic ring somewhere in your molecule. Now that's useful. There's another way that we can eliminate aromaticity by adding hydrogens, and that's called the Birch reduction. So you might remember from Chem 1 that alkynes can be reduced by dissolving metal reduction. So if we've got that alkyne, if we treat it with sodium metal, not ionic sodium, but just like actual sodium, in liquid ammonia, again, that's not aqueous ammonia that we usually use, but the anhydrous stuff that has a boiling point of like minus 50 or something, then you'll get an alkene. So we haven't reduced the alkyne completely, but partially. And so it turns out we can actually do kind of the same thing to benzene. So if we take benzene and do the dissolving metal reduction, we don't get cyclohexane, but we do get 1,4 cyclohexadiene. So kind of interesting. It doesn't reduce it all the way, but it does break the aromaticity, and it even breaks the conjugation. So those two double bonds are not in conjugation. But this can be useful because now you've got two separate alkenes, and if your molecule's symmetrical, maybe this isn't quite as helpful, but if you've got stuff attached in various positions, now you can use one alkene, you can do an addition reaction to that alkene to add functional groups to your molecule, and then you can separately do the other alkene. And that's certainly not something you can do with benzene. The only caveat here is that when you've got something attached, the carbon that it's attached to doesn't get a hydrogen. Okay, so what does that mean? That means that if we've got something on our benzene ring and you do the Birch reduction, we get that product where the R group is still on one of the carbons that's got a double bond instead of one of these two carbons here that has two hydrogens on it. So this is in contrast to that, where an extra hydrogen has been put onto the carbon that the R group is on. questions on hydrogenation and reduction of benzene? Okay. That's all of chapter 17. So let's kind of go through, how do we feel on, oh, that's just naming, isn't it? How do we feel on naming? Is that okay? Most of these you just look up. But we, for example, this one would be, what's the parent for this? So it's been, the parent's going to be benzoic acid. And we've got a chlorine, and it's at what position? Which is orthometapara. Which one is it? Ortho. So it's orthochlorobenzoic acid. J? What? Oh, did you figure it out? Yeah, okay. All right. Okay, how about this one? So, is there one you want to walk through? O? Well, that's O. Oh, okay. I like O. So, this is kind of like the example that we did with pyridine and pyrrole, where sometimes the lone pairs were important and sometimes they weren't, and it kind of didn't. Okay, so the key here is to draw out the lone pairs. So nitrogen. So we've got a lone pair there, and a lone pair there. So these sorry, other way around. Those are part of the conjugated system because, for example, we could draw a resonance structure where these move down and become a double bond, and then this double bond moves and becomes a lone pair. But this nitrogen is attached to a double bond. And so that lone pair is not conjugated. So what does that mean for whether it's aromatic or not? So we've got, okay, so the rules are the ring, yes. The planar, yes, you can assume that all of these are planar. 3 have conjugated pi system. Yes, it does. So these two double bonds are conjugated to each other. And because this nitrogen up here has a lone pair that can participate in resonance, it is conjugated. And then Huckel's rule is 4n plus 2. In other words, an odd number of pairs of pi electrons. That's another way you can think about Huckel's rule. And so These are not pi electrons that are in the system, but these are. So we've got 1, 2, 3 pairs, which is an odd number. That would satisfy 4n plus 2 because, let's see, if n is 1, then 4 times 1 plus 2 is 6 electrons. 6 electrons is 3 pairs. And so it does satisfy Huckel's rule. So that's it. Ooh, what about J? Yeah, it is aromatic. So
It's because electrons, right? Sorry, it needs electrons.
yeah, well, so obviously I, J, and K are all kind of the same molecule, just with different stuff going on at the carbon at the top. So I does not have a conjugated pi system. It's just a double bond. J does have a conjugated pi system because we can draw a resonance structure where pi bond, say, moves over. So the pi bond ends up there, and we get a positive charge there, which, of course, same molecule, but we drew a resonance structure, so that is conjugated. And then with K, you can do the same thing. You can take there's a lone pair on that carbon. Draw a resonance structure like that. And so that one's conjugated as well. So then all you have to do is look at the number of pi electrons. So this one, there's 2 electrons, the lone pair on that carbon, and then there's 2 in the pi bond, so that's a total of 4, which does not satisfy Huckel's rule. And then J, there's no electrons up here on that carbon, no pi electrons up here on the carbocation, but there's 2 in the pi bond, and that satisfies Huckel's rule, because 4n plus 2, if n is equal to 0, then it's 2. So that is aromatic. This one is anti-aromatic because it passes all the rules except Huckel's rule. And then this one is non-aromatic because it's not even conjugated. Any other questions on determining aromaticity? Yes? Yep. Same thing. The only difference here is the number of pi electrons. So this one is non-aromatic. These two are either going to be aromatic or anti-aromatic, but which one is which? So J was aromatic because it had 2 pi electrons. F is sort of the same case, but it's got 4. Does that satisfy Huckel's rule? No, so that's anti-aromatic. G, well, okay, K, failed Huckel's rule and was anti-aromatic because it has 1, 2, 3, 4 pi electrons. G has 2, 4, 6, and so it is aromatic. Okay, if you want to stay and chat about the homework, you're welcome to, but otherwise we are done for today and we'll start chapter 18 next time. Due dates for the homework are still as scheduled, so you don't have to turn stuff in early because we got done early.
Like